let's get started. It must be Friday. That's what it is. Everybody's taking their time. What I was saying, where is everybody? Maybe there's like, what's that?
Everyone who matters is here.
Now, come on. It's funny. My advisor in grad school, he was teaching a structural analysis class, and I guess there was supposed to be, I don't know how many people showed up, and he walks in and there's only 5 or 6 people there. He gets all angry and gets close, like yelling at everybody, and they go, "But we're the ones that are here. Why are you yelling at us?" He's like, "That's a good point. Why am I yelling at you? Y'all are the ones that showed up." Okay, just real quick on announcements. So homework 8 has been graded, and I gave that back. Did everybody get that? Okay, all right. I don't really think there's anything major to report on the solution. I mean, pretty much everybody did fine on it. The only thing that I think popped up quite a bit was on problem 2, the cover factor. A few people didn't apply it, but that was it. It was very minor. Don't forget homework 9 is due next Friday. No late submissions, obviously, because that's our last day of the semester, or last lecture of the semester, and I'm giving you the solution that day. One thing that'll be clear today is your final problem on that assignment will require the use of what's called an interaction diagram. We'll talk about that today. The interaction diagrams are uploaded onto Blackboard, but you kind of need to draw on them. So I'll have some hard copies on the cart outside my office. I'll probably try and print those today, or at least the ones that you need. One thing I will mention, on Monday, depending upon where we get, it might have been a good idea to have them today. I probably should have mentioned it. But on Monday, if you don't, bring a straight edge, because you will use it probably on Monday. So, and if we get to it today, we probably won't. So we'll get close. Don't forget your course evals. To date, I checked this morning. 13 of you have done them, and 12 of you have uploaded the screen capture of your completed survey list. So first off, if you're the person that did it and hasn't uploaded it, upload it. Again, free points. And if you haven't completed it yet, please just make sure and complete the survey by next Friday. And if you upload by the final, I'll get you 10 bonus homework points. Before I pass the sign-in sheet out, there is one thing I did want to mention. On May 12th, now I know this is after the semester is over, but if anybody is still in town, I thought I would mention it. On May 12th, we are hosting the annual West Virginia Bridge Design and Build Contest on campus. That's a Saturday. It's in this building, and it'll be all day. Honestly, I could use a few student volunteers. So first off, if you're in town and you're interested, let me know. And let me know by indicating on the sign-in sheet. No promises, I'm working on it, but there might be some money involved as well. So, but if you're in town and you're interested, let me know. So just put, like when you sign in, just say, on the side, like put me on the list. Because honestly, I could use quite a few volunteers, and it would help. It's on Saturday, May the 12th. I probably should put that on here, but it's on Saturday, May the 12th. It's after the semester's over, but it's on campus. It's in this building, and it'll be from early in the morning till the afternoon. It'll be a day thing. We'll feed you for sure. So, but just if you're interested. All right, sound good? Any questions? That's a good question. All right, so it's, like I said, it's an annual competition for middle school and high school kids. And honestly, there's going to be two main activities that go on campus. We're going to be doing the West Point Bridge Design software competition. Has everybody heard of that? Okay, and going to be testing of balsa wood bridges. So honestly, just having some hands on deck with, making sure that goes smoothly, just stuff like that. There's going to be around maybe 80 or so middle school and high school kids here, so just helping out. So.
What if you could only be here for like the first half?
Yes. I'll take any help I can get. Yes, absolutely. But put that on the sheet, so let me know. No. I think they'll have like T-shirts and whatnot. If you're interested and your name's on the list, like I'll probably send emails out to everybody to get sizes and whatnot so that they have shirts for everybody, because they're keeping it sort of like color coordinated. Like the middle school kids wear these shirts, the high school kids wear these shirts, the judges and the volunteers wear these shirts. So everybody knows who everybody is. So yeah. But yeah, any help would be greatly appreciated. Okay, sound good? All right. Before we get started, well, I'll tell you what. I have a few homeworks for those of you that came in late. Now I'll hand them out at the end of class. So, but it's the end of the semester. I will forgive you, but only this time. Okay. Let's get back into concrete design. So, if you recall, we were in column design mode. So we've already done column analysis problems and we're in column design. We've already designed one square column and we now need to design a circular column. And for the most part, we were done with this problem. We only have a few loose ends that we need to tie up. One of those loose ends is spirals. Sorry, spirals. I said stirrups. I don't know why. But we've already determined the size of the column, and we've already determined the amount of longitudinal reinforcement. So let's go back to that. So here's the column, and so we had FC prime is 4K, FY is 60. We use a reinforcement ratio of about 2% for our initial design. Now that changed a little bit. Let's see how that changed when we go through these calculations. Now remember, when we did the math, we got a column dimension of 18.4 inches that was required, but then we rounded that down. So what do we think is going to happen to our actual reinforcement ratio? Do you think that's going to go down or go up from 0.02? It's going to go up because we're using less concrete. So it should go up. We'll see what that does here in a second. Now we also solved for the required area of steel, and it sort of perfectly came out at 6 number 9. So we're using 6 square inches of steel where we needed 5.997. That sort of came out perfectly. So maybe what we should do right now, let's just go ahead and do this. Let's just go ahead and check what is our actual rho G. So it's the area of steel divided by the gross area of the column. And that's 6 square inches divided by, now what's the actual gross area of the column? No. It's 254.5. That's, okay, and let's make sure everybody's clear on that, okay? The actual column that we are using is an 18-inch diameter column. It's not the required AG min. Remember that AG min was based off an assumption, so just got to make sure you're using the right value. So what does this come out to be? There we go. So 0.0236. Do I have a second on that? So it did go up a little bit. We were using 0.02 for estimation, but it did go up. Now, is that fine? Yeah, and why is it fine? It's between 0.01 and 0.08. So that's totally fine. So. Okay. Is everybody okay on this? Okay. I'm going to go on to the next panel because there's only one thing left to do for this column, and that's determine the stirrup layouts. I said stirrups again. It's spirals. What? I was here somewhat early this morning, so maybe my coffee's wearing off. Maybe that's what it is. Okay. So let's look at spiral selection. And to start off, we need to pick a size for the spiral. And unless you're using like really, really large longitudinal bars, I think a pretty safe assumption is to always try out a number 3 spiral. That's a very, very common spiral size. And I'd say, unless otherwise noted, you can go with a number 3 spiral. So if we're going to use a number 3 spiral, we should know that the diameter of that spiral is 3/8 of an inch. And the area of that spiral, what's the area of a number 3? 0.11. Okay, that, we're going to have to fix that because that looks just like another D. 0.11 square inches. Okay. All right. Now, another thing that we haven't discussed really for this column is cover. So unless otherwise noted, what's arguably the most common cover dimension that we're going to use for columns? 1.5 inches. So unless otherwise noted, 1.5 inches is always the way to go. So we're going to say assume 1.5 inches of cover. Okay. And the reason why is because we need a core diameter. Okay. Now the core diameter, we take the actual diameter of the column and we subtract how many covers? 2, right? Because we have 1 on each end. So we have, here's the column and here's the core, so we go N1 and N1. So 2 cover. So that's, now what was this, an 18-inch diameter column? Minus 2 times 1.5 inches, so 2 times 1.5 is 3, so that's 15 inches. So the area of the core is pi over 4, the diameter of the core squared, which is pi over 4 times 15 inches squared. And what's that? 176.7, we'll just leave it there, inches squared. Do I have a second on that? Okay, and so the area of the core is 176.7. What was the actual gross area of the column? It was 254? 254.5. Okay, all right. So the way that we're going to assess this is as follows. So what we're going to determine is rho S min first. In other words, what does ACI state is the minimum amount of spiral reinforcement that we have to provide? Okay, and that is the 0.45 AG over AC minus 1 times FC prime over FY. Does everybody remember that? So this comes from ACI. ACI says you have to provide at least this much reinforcement. Okay, so plug and chug, we get 0.45. Now this was 254.5. Did I do that right? And this is 176.7 minus 1, and then 4 KSI over 60 KSI. So first, give me 1 sec. So first off, what are the units going to be? Unitless. Okay. All right. And then while we're working on the value, what'd you have? Oh, yeah, no, it's the same bar, yeah. So if you have a column, it's not going to go like number 3, number 6, number 3. It's always going to be one consistent size. So what are we getting? Does anybody have a number here? Okay, all right. So that is the percentage of steel that we have to provide, okay? Now, how do we determine how much spiral we need? Okay, well, let's see if you all remember this. You remember that to compute, I'll call it rho S actual, that is the volume of steel divided by the volume of concrete, and we had derived a formula for that, and that was 4, and it was AS, and it was DC minus dB, or ds, sorry. And then it was S dC squared. Do y'all remember this? So this is how we determine the actual percentage of steel in the column. So this is what's actually there, and this is how much we have to provide. Well, look at this formula. What's the one variable we don't know? Well, no, we know that because we know we're trying out a number 3 spiral. What don't we know? The spacing. We don't know how far those spirals are to be spaced out. So let's solve for S. So after you do a little bit of algebra, bless you. So after you do a little bit of algebra, you're going to find that S equals, let's see, 4 AS DC minus DS, and then rho S DC squared. Does that make sense? All I'm doing is literally just taking this here, just swapping out the S and the rho. And what I'm going to do is I'm going to plug in this value of rho to determine what my spacing needs to be. So that is, so we got a big fraction here, 4 times 0.11 inches squared. We got 15 inches minus 3/8. And then on the bottom, we're going to use that 0.0132, and then we're going to have 15 inches. Now don't forget that 15 inches on the bottom has got to be squared. We'll say 2.17. Do I have a second on that? So is everybody okay with that? Now let's think behaviorally, okay? What this equation is saying is that is the required amount of spacing in order to achieve this required reinforcement ratio. But nobody's going to spec out 2.17 inch spiral spacing. They're either going to round up or round down. So you tell me, should we take this value and round it down to 2 inches, or should we round it up to, say, 2.5? What do you think? Should round it down, right? Because we're trying to determine the minimum amount of steel. Okay, if we round that up, that would essentially be providing less steel. Okay, to be conservative and to provide an adequate amount, we need to round that down to 2 inches. So therefore, I propose that the design for this column is as follows. And please don't judge my inability to draw a circle. Okay, so because there's a lot of them. All right, so we have that. Well, just wait. It's going to get worse. And then 1, 2, 3, 4, 5, 6. That's the best you're going to get, and we're just going to go with it. You need to. All right. So we have a column that is 18 inches in diameter. We have 1.5 inches of cover. Now our spirals, we have number 3 spirals at 2 inches, and our reinforcement is 6 number 9s. And there you go. Oop. It's really not that bad, is it? I mean, this column design stuff is pretty straightforward. Are there any questions? Okay, all right. Now on to our final test topic. And for the rest of class, this is probably going to feel a little bit like movie time, but I really want y'all to pay attention, because in terms of some of the calculations, I'm going to bring it back to some stuff we did a while ago, and I'm also going to do some things that might be a little strange when you first see it. But I think you'll find, once you break it down and think about it, it's really not that out there. Okay, so first off, let's talk about beam columns. Let's sort of explain what's going on. Okay, so we've talked about beams before in this class, and we've handled beams, you know, ad infinitum. We did T-beams, doubly reinforced beams. We did singly reinforced beams. We did design. We did analysis. We did a boatload of work looking at moment strength, right? At phi mn or mn. Okay. Now, I would argue if I could sum up one principle in one simple statement that you need to analyze a beam, it's this. C's got to equal T, right? Compression has to equal tension. In other words, that's how we determine the moment capacity of a T-beam or a doubly reinforced beam or a singly reinforced beam or what have you. It was all hinged on C equals T, right? So I want you to think about that, keep that in your mind, the concept of C equals T, all right? Now, another way of writing that, if C equals T, would you agree C minus T has got to equal 0? Okay, all right. I know that might seem a little weird, but there's a reason why I'm writing it like that, okay? Now, there's a little bit more going on than that because you've got, well, the concrete is 0.85 FC prime in compression. The steel behaves linearly up until Fy and what have you. But I just want you to keep that stuff in your head because we're going to refer to it a little later. Okay, let's talk about this concept of interaction, okay? Now, let's look at a column, okay? Now, I got a column. I'm putting a load on it. There's always two sides of the expression. There's the resistance, right? There's phi Pn. Phi Pn is the amount of load that column can withstand before it's going to fail. And then there's Pu. Pu is the amount of force that we are putting on that column. And as long as phi Pn is greater than or equal to Pu, we're good, right? Okay? Now, another way of writing that is to write it in terms of like an efficiency. If we take Pu and divide it by phi Pn, as long as that value is less than or equal to 1, we're good, right? And that's sort of a design efficiency. Everybody okay with that? Similarly, we could do the same thing for moment, right? We could have an mu over phi mn has to be greater than or equal to 1. But now, here, this comes the kicker. What happens if we have both on the section? What happens if we have axial load and moment on the section? Well, I would argue that you can't really expect, if I have bending moments and axial load on an element, I can't really expect to get 100% of the capacity out of the axial load and 100% capacity out of the bending moment simultaneously. But if we're looking at just axial load, if that ratio has to be less than or equal to 1, and if we're looking at bending moment and saying, well, that relationship has to be less than or equal to 1, if we've got both on there, I'd argue a very, very simple, what I'd call interaction relationship, if I have both on the section, is that this ratio plus that ratio has to be less than or equal to 1. This would be arguably the simplest way to write what's called an interaction relationship. In other words, if I've got a column that's got, or if I've got an element that's seeing axial load and bending, I can resist a little bit of axial load and a little bit of bending as long as the sum of those is less than or equal to 1. Would that be a fair statement? This would be a very, very simplified expression of interaction. The idea that those two forces are interacting together and we have to be able to resist both of them safely. Now, the problem with that expression is it greatly, and I mean greatly, underestimates the combined capacity of a reinforced concrete column. And here's the main reason why. Let's say you have just a beam by itself. You're bending it. So some of that beam's in compression, some of that beam is in tension, right? Okay, what is concrete not like? What does it weaken? Tension. Okay, so imagine if I took that beam and I applied some compressive force to it. Do you think its bending capacity would go up or go down? It'd go up, right? That's the main fundamental principle of pre-stressed concrete. The idea that concrete does not like tension, so we'll just apply extra compression to it. And you can actually get additional capacity out of a reinforced concrete element if you apply additional compression, okay? And what I want to do is I sort of want to show you how that works through an illustrative example. I want to take a representative section, and I want to draw an interaction diagram, an actual real interaction curve. And I'm going to show you how these calculations work, and I think you'll find this is pretty straightforward. Now, I got a column here. It's got 4 KSI concrete. It's 60 KSI steel. Each of these bars are number 9, so I've got 4 number 9s in the section. And let's see, so the column's 18 inches by 18 inches. We'll say the cover is 3 inches all around. And we'll say that it's being bent this way. It really wouldn't matter for this column if it was being bent this way because the column is symmetric, okay? But if I had a column that was longer one way than it is another, obviously it's going to be weaker in one direction. So, but for our purposes and just to explain what's going on, let's keep this simple. So we'll say we're bending it about that dashed line, about the x-axis, if you will, okay? So what I want to do is I want to start defining points on this curve, and I sort of want to plot that out, okay? So let's start off with the case of just pure axial load, okay? So if there's pure axial load, there's no bending moment, the bending moment equals 0, okay? How do I determine the maximum axial load that this column can take? Well, it's this right here. Now, you all should be very familiar with this expression. We've been using it very, very recently. 0.85 FC prime times the area of the concrete plus Fy times the area of the steel. Now, I'm not applying my phi values. I'll do that later. And I'm also not applying this 0.8 for accidental eccentricity. I will do that later. But for now, I'm keeping everything theoretical and keeping it straightforward. Everybody okay with that? So one point on this curve would be m equals 0 and p equals 1328. Everybody okay with that? So think if I'm collecting points like x comma y, here's some x comma y data right here. So that's a simple one, okay? Another simple one is, now let's look at the flip side, okay? Now let's look at the flip side where there's no axial load and it's just pure bending. Well, if that's pure bending, I don't know about you, but that sort of looks like a doubly reinforced beam, right? Doubly reinforced beam where part of the steel, or we have steel that's in tension and we have a steel layer that's in compression. Remember this equation right here? Remember that? That's how you determine where the neutral axis is. Remember that? So take this equation, start doing, here's our, ax squared plus bx plus c, plug and chug, set that equal to 0. So I have c is 2.691 inches. Take that c value and say, all right, let's go through and, a is, what is it, beta 1c, and then here's our moment capacity. Do y'all remember that? I know it's been a little while, but I know we did that. So when you plug and chug, do all the math, do all the units, so on and so forth. So we've got a bending moment of about 141.65 foot kips, okay? So now we've got 2 points on the curve. We've got the case of pure bending and the case of pure axial load. But what about the points in between? I mean, you got to understand, we're trying to define a whole curve, okay? How do you figure out the points in between? Well, a very, very easy way of doing this, and let me preface this, if you were doing this for real, the magic word is Excel, okay? Because Excel can do calcs over and over and over again, okay? So an easy way of defining the remainder of the curve is to actually just guess a C value, okay? Remember C, sorry, let me go back, sorry, right here. Remember C is where your neutral axis is, okay? An easy way of doing this is just guessing a C value, okay? Now, sorry, let me go back here. So once you guess a C value, you can take that C value and you can determine strains. Once you determine strains, you can determine stresses. Once you determine stresses, you can determine forces. And then you can just use equilibrium to determine what's going on with the rest of the with the rest of the curve. So I'm just going to, for the sake of discussion, I'm just going to make a random guess and say that C equals 11 inches. There's nothing magical about that value because I'm going to do it for a whole range of C values. I'll actually show you the Excel sheet here in a second. But let's just, for the sake of discussion, let's just say C equals 11 inches. Okay? Now, if C equals 11 inches, let's just say if, then here's how we would determine the strain in the upper layer of steel. Here's how we would determine the strain in the lower area of steel, right? So look at these strain values, 0.00218, 0.00109. Is this upper layer yielding? Yes. Is the lower layer yielding? No. Okay? So we've got a situation where the upper layer yields, the lower area, or the lower layer doesn't. So the upper layer, the stress is 60 KSI. The lower layer, the stress is E times the strain. Everybody okay with that? Okay, now if I've got the stress, I can determine the forces, right? 0.85 FC prime times the area in compression, so that's 0.85 FC prime AB, and this is A, beta 1C. And then for the steel, it's just the area times the stress. For the compressive steel, it's 60 KSI, and for the tensile steel, it's this. Everybody with me so far? Now, here's where it gets crazy. Does C equal T? No, it doesn't. Because we're not dealing with a situation that has pure bending. In other words, C minus T does not equal 0. In this case, C minus T equals whatever axial load we're putting on it. So that's where the equilibrium comes into play. So if you take C minus T, it doesn't equal 0, it equals 628 kips. That's the axial load that we are putting on the section. The bending moment is just summing moments, forces and moment arms, summing them up and accounting for your units. So when it's all said and done, right now we have a few points. Okay, we've got our pure axial load case, our pure bending case, and then a point in between. You can write a spreadsheet, and this really isn't that difficult to write a spreadsheet to handle all the points in between. Okay, so let me see if I have that. I think I have it here. Oh, I have it here. Yep. Come on. Okay. So here what I've done is I've just guessed a whole bunch of different C values to plot this curve out. Now the one I showed you was the one at C equals 11 inches. There's nothing magic about that one value. I was just picking a whole bunch of them. So the top row, if you look here, the top row, this is the case of purely axial load. And then this case here on the bottom, that was the case of purely bending moments. So if you do your pure bending case, and you know for your pure bending case that C equals about 2.69 inches, you can know to sort of start here and go up and up and up. And you'll get to a point where you could keep going until C kind of goes to quote-unquote infinity. And if C equals infinity, that's just your pure axial case. But for each one of these rows, what I'm doing is I'm saying, all right, here's a C value. Based on that C value, what are my strains? Based on those strains, what are the stresses? Now look at these formulas here for the stresses. Actually, let me do something. We go to File, Options. So you all can read what's going on. There we go. Okay, can y'all see the formula? Is that a little better? Okay, so for each one of those C values, I'm saying, okay, what's the strain? 0.003, C minus D over D prime, all that. Look at my formulas for the stresses. It's either Fy or it's E times the strain. So that's just a simple if statement. Look at my, compressive force in the concrete, 0.85 FC prime times AB. Look at my force for the compression steel and the tensile steel, just area times the stress. These formulas right here, these are just my moment arms. So I'm calling them Z distances. I can call them whatever. And then for the axial load, just sum up all the forces. For the moment, I'm using what's called sum product. So what sum product is doing is it's saying this times this plus this times this plus this times this. And that's just sum of moments, right? Force times distance, force times distance, force times distance. So this really isn't that difficult when it's all said and done. Now, if you take these values and plot them out, x comma y, you're going to get a curve that looks something like this. Okay? So this is what's called a PM curve. You'll hear it termed PM curve. You'll hear it termed interaction diagram. That's what this is. This is an interaction diagram for a typical section showing the relationship between a section's axial force capacity and a section's bending capacity. Now, do you remember that very, very simple interaction formula I showed you earlier? It was like P over phi Pn plus M over phi Mn has got to be less than or equal to 1. That is just this line right here. But that in no way, shape, or form represents what's really going on. Reinforced concrete elements can withstand bending moments and axial loads far beyond that. See, like for instance, what's happening down here, oh, sorry. What's really interesting is what happens from like right here till about right here. This is a really interesting region in the element, because this right here, this is the section's pure bending capacity with absolutely no axial load on it at all. And we got something like 145, 146 foot kips. But then you take that section and you start applying a little bit of axial load, and you're applying axial load. That load's in compression. That's helping the element out, because you're applying that compression, you're negating some of that tension. So by applying a little bit of compressive force, you're able to up that bending capacity quite a bit. It's pretty interesting how to see what happens when those loads evolve. Now, for practical purposes, there's a couple things that we need to do. I want you to pay attention to this. So here's the nominal curve. Here's what I'm calling my cutoff curve. So y'all see this and this? See that? And what's happening is I'm adjusting that by an alpha value of 0.8. And the way that we handle that is we basically say, I don't care what this says. Accidental eccentricity says that that capacity cannot go above 80% of the theoretical axial load. So any value that's over 80%, we just cut that off. Okay? Everybody okay with this? Now, there's one other value I forgot. What's that? What? Say it again. Phi value. We did not apply the resistance factor. Okay? So here is the nominal cutoff curve. Now I want you to watch this. Here's the nominal curve. There's the design curve. So that's actually applying the phi values. Now if you notice, it gets kind of weird right here. You get this sort of little nubbin area right there. Okay? There's a reason for that. Okay? I want to show you something. First off, there's a pretty dramatic shift between here and here, right? The reason why is because for most of the range of the curve, my phi value is what? What's the phi value for columns that we've been using for square columns? No, that's for circular columns. 0.65. Okay? But now let's scratch our noggins a little bit. What does phi actually look like? What is the curve for phi? Let's see if y'all remember. Let's see. Y'all remember this? This is what phi actually looks like. For compression regions, it's 0.65, but under pure bending, it's 0.9. There is a region where it transitions. Everybody remember that? So if you look at your phi values, let me go to the, actually Excel, let me go here. Look at this. This is my design curve. And if you notice, for most of the curve, it's 0.65. But there's a transition region. There's a region where that jumps between 0.65 and 0.9. So that's what happens here. You get this sort of little nubbin area right here. That's why it sort of looks weird. That's where it's transitioning from 0.65 to 0.9. Right. Does that make sense? Now, I know that this is obviously one of the coolest things you've ever seen in the history of this class. That was a joke, not a very funny one. But I'm sure some of you are kind of like, oh, that's great, Dr. Mike, but where am I going to use this? Like, where does this matter? Let me skip ahead to right here. Okay. Well, if you understand that process, what I want you to understand is how we can use these curves to design beam columns. Okay? That curve that I just showed you, the problem with it is that was a curve for a very specific beam column under very specific dimensions. I'd like to be able to use something that's a little more generic. Fortunately, ACI has derived a bunch of generic beam column interaction charts for a series of dimensions. Okay? I'm actually going to pass these out. There's a whole lot more uploaded to Blackboard, but these are the ones that we're going to need for our example in class. So 1, 2, 3. There's that. One, two, three, 4, 5, 6, 7, 8. Okay. Oh my God. My goodness. It's the end of the semester. That's what it is. All right. Okay. So in practical terms, if we had to do or derive an interaction chart for every beam column that we would ever see for any situation at any time, that would be a pain in the butt unless we had a very, very well-refined Excel spreadsheet, which, I mean, there are Excel spreadsheets out there that can do that. But for practical purposes, if you're just trying to determine the amount of reinforcement that needs to go into beam columns, that's what these interaction diagrams are for. Okay? So there's a couple things to point out. First off, if you notice, basically you've got a bunch of interaction diagrams that are plotted in front of you, but look at the reinforcement ratios. Does everybody see the reinforcement ratios on the left? Where do they go from? Over here on the very left, up top. They go from 0.01 to 0.08, which is the ACI limits for compression elements. So right off the bat, the interaction diagrams are limiting you to what's going on for a given column based on ACI requirements. So it's limiting you to that. Another thing that you will notice, and this is one of the reasons why these charts are so useful, is that they're essentially dimensionless. What you do is you compute these two dimensionless quantities, this Kn and this Rn. The Kn is sort of related to your axial load effect, and the Rn is related to your bending moment effect. But if you follow the units, you will find that these terms are dimensionless. So because of that, we're able to use these charts for a number of different beam columns because it's not as heavily dependent on individual dimensions. It's just a lot of algebra and a lot of plotting and a lot of time. But you know, that's sort of where these things are developed. So these are very typical beam column interaction charts. We've got beam column interaction charts for rectangular elements, for circular elements, and what have you. And I'm going to sort of teach you how to interpret these. They're really not that bad once you take some time and digest them a bit. Okay? So first off, if you look here on the top, it says interaction diagram, and it says on the handout that I gave you, it says interaction diagram L4-60.7. Does everybody see that? And if you look on the back, it says L4-60.8. Does everybody see that? So let's see if we can Sherlock Holmes this and figure out what do you think the 4 and the 60 correspond to? Well, I'll get to it. I promise. I promise. I know what you're getting ready to ask. I know what you're getting ready to ask. Well, let's take this one step at a time. What does the 4 and the 60 stand for? FC prime and FY. So right off the bat, that'll tell you what material strengths these charts are valid for. Now, what about the 0.7 and the 0.8? What do you think that corresponds to? This gamma term. And what is gamma? It's basically the relationship between the dimension of the column and the dimension between the layers of rebar. Okay? Make sense? Okay. Now, the one question is what's going on with the L and the C? Well, first off, the C is pretty simple. C stands for circular columns. But what's going on with the L and the R? Okay? The L corresponds to rectangular columns that have 2 layers of steel, and R stands for rectangular columns that have 3 layers of steel. So a very simple example would be this is an L column. That's an L column. And here is an R column. That would be an R column. And if you think about it, think about this from an equilibrium standpoint. You know, if I'm summing moments about, let's say, this neutral axis, I've got the compressive force in the concrete, I've got the force in this layer of steel, and the force in this layer of steel. Whereas if we're talking about R columns, I've got the force in the concrete, and then this layer, and this layer. And because the neutral axis shifts, these stresses aren't zero. So the way that we compute our moments, and ultimately the way that we would plot that PM curve, is going to be a little different. Okay? So, for instance, if I'm dealing with chart L-460 or L4-60.7, that's a rectangular column with 2 layers of steel. The FC prime is 4 KSI, the FY is 60 KSI, and the 7 refers to that gamma ratio. So if I had, let's say, a column that was 20 inches deep, and the distance between the 2 layers is 14 inches, 14 over 20 is 0.7, I'd use that chart. Okay? Does that make sense? And did that answer your question? No, I printed off the ones that you would need for this example. That's why I did that. Okay? So let me explain the procedure for beam column design. Beam column design, you're primarily sizing the element based off of either axial loads or available formwork and whatnot. So usually when you're designing beam columns, you're dealing with a situation like this where you already know what the size of the column is going to be, and you just need to determine the amount of steel. So it's pretty straightforward. You determine a factored load, your PU and your factored moment MU. So once you've got those, determine a required nominal load, and we do that by dividing by 0.65 or 0.75. In most of the ranges for a beam column, you're dealing pretty much in that 0.65, 0.75 range for phi. That's a pretty valuable assumption. Once you've got that, determine your eccentricity, and I'll explain that a little bit better on Monday, because I think I'm going to call it after this, but determine your eccentricity and your gamma parameter. Once you've got that, determine these, go into your charts. Now let me show you why I printed off the charts that I gave you today. Help me out. What's the gamma value for this problem? What do you think? Now, how do you determine gamma? Look at this. Say it again. The rebar. No, it'd be 20 over 15. Okay. Or, and no, it'd be the opposite. It'd be 15 over 20. What is 15 over 20? Say it again. It's 0.75. So which one do you need? You need the value from the 0.7 chart and the value from the 0.8 chart, and then you average them. Hold on. Hence why I gave you the 0.7 chart and the 0.8 chart. We're just going to use both charts, interpolate, go from there. All right. A couple things. Bring this on Monday. What do you think you need now on Monday? Straight edge. Bring a straight edge on Monday. 2 other points. Number 1, I am going to bring, no, I'm not going to bring snacks. I am going to, actually I'll probably do this today. I'm going to print off the necessary beam column charts that you need for your homework. I'm going to put them on the card outside my office so that you'll have them, okay? Don't worry if you need beam column charts in the exam. I'll have those provided as well. I'm not going to make you print these off. Number 2, we're going to do this example on Monday, and then we are done with exam 3 material for reinforced concrete design. On Monday, we can recap. If you all have any particular topics you'd like me to talk about on Wednesday, I'd be happy to do that. It's not going to be completely voluntary, and you don't have to come if you don't want. And Friday, we will have our exam review, and then we are done with this class. That was pretty good. That was pretty good. All right. You all have a wonderful weekend. I will see you on Monday.